So we discussed the torque in the case of electromagnetic circuits. See, so torque, yes, and we will draw a simple schematic which shows the direction of forces 1, 2, 3, and 4. And basically, when we're talking about a circuit, electromagnetic circuit, it's something like this. Yes, we have a solenoid, the current flows here, and then we have this thing going on, which is electric field, magnetic field, and force, which are three different but interdependent parameters. Yes, so the situation here is that if we define this distance to be b, yes, so we have a situation where see, the force 2 goes here, and force 4 goes here. Here we have this distance, which is b, but half of this distance is b by 2 on both sides. So torque is equal to, you see, force into distance, couple where the rotational effects are added, f2b by 2 plus f4b by 2. Yes, it's understandable if this is the center here. So force, as we have established in general, is equal to IAB. Yes, IAB. ILB, but ILB sine theta. Sine theta can be 1 when theta is roughly 90 degrees, and L can be A with this dimension. We substitute the variables. Yes, so see, torque is equal to IAB B by 2 plus IAB, since forces are equal in all the sections of this diagram in this circuit, B by 2. Yes, so tau is equal to 2IABB by 2. So 2 cancels out, obviously, and AB is equal to A. Now these two dimensions multiply and give us the collective area. So tau is equal to IAB. Yes, approximately. And this is when we have, let's say, one number of turn. So if we have multiple number of turns, so the tau would be NIAB, where n is the number of turns. Yes, and when there are approximations with the angle, we can introduce, as we know, angle from here, IAB sine theta. So we will introduce the angle tau is equal to NIAB sine theta. Well, when theta is if it is 90 degrees, then sine theta will be 1, but otherwise we will have some value for this sine theta. So basically the general form for torque as we derive here is this. see tau. Yes, so here it is. So this is the equation, and when theta is 90 degrees, sine theta is 1, and IAB is the form once again as theta is equal to 90 degrees, sine theta is equal to 1, and that depends upon the orientation of the parameters E, B, and F, the electric and field and magnetic field, and then the force. Okay, so that's 90 degrees usually, but still there can be minor deviations in complicated situations, but we will ignore that for now. And once again, back to the simple form. If there is just one, if n is equal to 1, once again we get magnetic field, current, and then this A, which is the product of A and B, approximately the area covered by this coil mechanism, and this is the torque tau here. So in this case we put n is equal to 1. You see, so these are the basics of torque in an electromagnetic circuit. And just a small application of this torque in circuits, we have the example of a galvanometer, which is a measurement device. So in this case, the magnitude of torque is equal to NIAB sine theta, the general form as we know, and sine theta is approximately 1, so we put tau is equal to NIAB, yes, and this is the magnitude of the torque. This is the magnitude approximately. But then we know that there is this restoration torque as well, which is directly proportional to the angle that the needle rotates. Yes, and then if we get an equation out of this proportion, c theta, c is the constant of proportionality, theta is the deviation in terms of angle, and tau is the torque of restoration. So now we can equate these two. So we have this form, let's say we call it tau here. The magnitude with the theta is equal to 90 degrees, so sine theta is equal to 1. So we have equation 1 here, and then we have 2 here. So now c theta is equal to NIAB, and theta is equal to NIAB by c. Yes, constant of proportionality in terms of the restoration torque. And or once again, one more form is in terms of current. If we are to look into the measurement of the current, so c theta by NAB, so I is equal to c by NAB, which is constant, c by n number of turns, area, and b the magnetic field. This is somewhat constant, yes, so we can get an approximation in terms of a proportion that the current is directly proportional to the angular movement, displacement, or the deviation of the needle. So this is the principle of galvanometer as an example of torque in an electromagnetic circuit. Now we have a little bit on alternating current, AC. See, so we have the alternating current AC, and proposition is that voltage is equal to voltage maximum times sine of omega t. Sine of omega t, where t is the time and omega is the angular velocity, but that is mechanics, so we'll take this approximation where omega t is equal to theta. So we will simply use the form v is equal to v max, the maximum voltage, times the sine of theta. Yes, and see, in the alternating current we have this thing going on. The wave is not just on one side of the axis, but it's something like this, above and below. Yes, so the positive peak is here and the negative peak is here, you see. So this is the general depiction, and it can be explained further. So as we know, v is equal to IR, and then I is equal to v by R. Yes, so what happens is that we will put now the value of v, which we know from here. I is equal to v max sine theta by R, where R is the resistance and I is the current. And now v max by R, you see, will be v max by R, you see, will be I max, the maximum current. You see, so now we have this thing going on which says that I is equal to I max times sine theta. And we get into the root mean square for the, on this axis we have I, for example, and now we get into root mean square. Okay, so now we know that I is equal to I m I max, or I m, at sine theta or sine omega t. You see, omega t is equal to theta. Once again we make use of the substitution, and now we square the I, so we get I m square sine square omega t. Yes, and now this gets interesting. So we're taking a little bit of an arbitration here, and I square now is equal to I m square, and once we remove the sine square omega t, we are left with 1 by 2. So I square is equal to I m square by 2, and if we are to remove the square, then see, the situation is I is equal to I m by 2 under the root. Yes, so this is basically the root mean square, the maximum current divided by under the root 2. So this is root mean square And these are approximations which we incorporate. Just a little bit of modern physics now. This is electrical stuff, but now we need some classical physics as well, which is important here. So we look into the de Broglie hypothesis. Yes, de Broglie's hypothesis. So initially we know that energy is equal to Planck's constant times the frequency of the wave, and energy is also equal to mass times the square of the speed of light. Yes, we have these two, 1 and 2, and we equate the two. HF is equal to mc square. HF is equal to mc dot c. Yes, so